The Tunguska Event, often also referred to as the Tunguska Incident, marked the largest impact event in recorded human history. It took place near Russia's Podkamennaya Tunguska River on the morning of June 30, 1908. The blast size, equating to roughly 12 megatons, led to a phenomenal environmental impact. 80 million trees in the desolate East Siberian taiga were flattened across a shocking 2150 square kilometers. Casualties were low due to the remoteness of the region, but it is believed that the event may have claimed at least 3 lives, attributed to a meteor airburst, specifically the atmospheric explosion of a stony asteroid around 50-60 meters in size. The Tunguska event possessed a unique character. The asteroid is thought to have exploded about 5 to 10 kilometers above the Earth's surface, rather than causing a direct impact, thus leaving no identifiable impact crater. The event's sheer scale makes it a popular point of reference in discussions surrounding asteroid impact avoidance. The day of June 30, 1908 started with Evenki natives and Russian settlers observing a bright, bluish light in the sky that was almost as brilliant as the sun. Soon followed a huge explosion that lit up the horizon and spewed out a pillar of fire which painted the surrounding landscape in red. Around 10 minutes later, the skies echoed with sounds reminiscent of artillery fire, and shockwaves strong enough to knock people off their feet were felt several hundreds of kilometers away. The explosion left its mark across the globe, with its shockwaves registering equivalent to an earthquake of 5.0 Richter magnitude at seismic stations across Eurasia, and airwaves from the blast were detected as far away as Germany, Denmark, Croatia, the United Kingdom, the Dutch East Indies, and even Washington, D.C. In the aftermath of the event, night skies in both Asia and Europe glowed mysteriously. This is thought to have been due to light scattering from ice particles at high altitude as a product of shockwaves caused by the explosion. In the U.S., a Smithsonian Astrophysical Observatory located in Mount Wilson Observatory, California, reported a decrease in atmospheric transparency over a few months, an indication of increased dust particles in the atmosphere. The dramatic effects of this event have led it to be frequently referenced in pop culture and scientific discussions alike. The historical account of S. Simonov on the mysterious explosion near the Tunguska River, as documented by Russian mineralogist Leonid Kulik in 1930, drastically relays the intensity of the event. Sitting by the house at the Vanavara trading post, roughly 65 kilometers south of the blast, Simonov observed as the northern sky suddenly rent in two and became engulfed in flames, evoking the heat of the fire. Simonov described the searing temperature which prompted the desire to rip off his burning shirt. The moment was followed by a powerful noise, reminiscent of rock falls or cannon blasts, which caused the earth to quake, flinging him several meters away. Hastily, his wife led him to safety inside their home, while the blast left scorched tracks between houses and wreaked havoc on their crops also. It damaged buildings, breaking windows and snapping an iron lock of a barn. Set on a similar backdrop, I.M. Suslov's 1926 recording of a testimony of Shoshan of the Shanyagir tribe tells a story just as horrifying. Shushan, who inhabited a riverside hut with his brother Chekarin, recalls a strong wind accompanied by a peculiar whistles that forcefully awakened them by shoving. As the tumult outside the hut intensified, with trees audibly collapsing, Shushan was forcefully hurled into their fire. Their desperate calls for family proved futile against the sound of the first thunder. The severe winds toppled their hut and pinned Shushan down with sticks amidst the chaos. He bore witness to the falling trees, their ablaze branches, and a fierily bright sky, comparable to the Russians' description of lightning. It was as if a second sun had risen. Further thunderstrikes followed with lesser intensity until they were distant rumbles. Agonizingly, the brothers struggled to free themselves from the ruins of their dwelling, while the observation of the horizon added to the terrifying spectacle. These lines were composed by an author who, at the time, was situated in a woodland area, approximately 6.4 km north of Kirinsk. The prominently heard sounds appeared to be a recurring artillery barrage, occurring from the northeast every 15 minutes, a total of 10 times at least in Kirinsk. The tremors caused the window glass of buildings facing northeast to rattle. When the meteorite hit, significant ground vibrations were observed, and in the Lova village, within the Kansk West, 2 booming explosions were reported, rendering the impression of heavy artillery gunfire. A peculiar atmospheric phenomenon was reported in Kezemskoye village on the 17th. At precisely 7:43 The hum of strong wind was heard, swiftly followed by a formidable thump and subsequent earthquake that rocked the buildings. The rumble was not solitary. A second, then a third thump reverberated, all amid an unusual subterranean rattling, reminiscent of dozens upon dozens of trains rumbling along the tracks at once. Subsequently, for a span of 5 to 6 minutes, the echo of what seemed like 50 to 60 artillery volleys fired in quick, equal intervals was heard. These echoes gradually diminished in volume. At a glance, the sky appeared clear, devoid of wind and cloud. On closer scrutiny toward the north, the source of the thumps, an ash-like cloud, was observed near the horizon, diminishing and fading until it fully vanished around 2-3 p.m. Since this 1908 event, the Tunguska explosion has been the subject of approximately 1,000 academic papers, predominantly in Russian due to the isolated location of the site and minimal instrumentation available at the time. Modern scientific analysis has primarily relied on data from geological studies and damage assessments conducted years after the event. Energy estimates range from 330 megatons of TNT and or 126 petajoules. Scientific investigation of the region did not take place for over a decade after the event, owing to extreme isolated nature of the area, coupled with significant political upheaval in Russia during the 1910s. In 1921, Russian mineralogist Leonid Kulik led a preliminary expedition to the Podkamenaya Tunguska River Basin under the aegis of the Soviet Academy of Sciences. Despite not visiting the central blast area, Kulik was inclined to believe that the explosion resulted from a colossal meteorite impact due to the accounts he gathered from local residents. This led him to convince the Soviet government to financially back an expedition to the potential impact zone under the pretense of salvaging meteoric iron. In 1927, Kulik led the scientific expedition to the Tunguska explosion site. Local Evenki hunters guided his team to the center where they expected to find an impact crater. The lack thereof was startling. Instead, they uncovered a scorched, branchless tree zone around 8 km in diameter, with the trees still standing upright. Trees further away exhibited partial scorching and were knocked down outward from the center, forming a striking radial pattern of fallen trees. Over a span of a decade, Kulik spearheaded 3 further expeditions to unravel the mystery of the region. He discovered several small bogs, initially believed to be meteoric craters. One such crater, specifically Suslov's crater, was exhaustively drained only to have a tree stump at the base. Discounting the possibility of it being a meteoric crater, Kulik also organized an aerial survey in 1938 that encompassed the core section of the flattened forest. However, the original negative strips of these aerial surveys were destroyed in 1975 under the orders of Yevgeny Krinov, the then chairman of the Committee on Meteorites of the USSR Academy of Sciences, to eliminate the highly combustible nitrate films. Thankfully, the positive prints were safeguarded for future studies in Tomsk, Russia. Later, expeditions in the 1950s and 1960s discovered microscopic silicate and magnetite spheres and soil samples from the area. These spheres were expected to be present in the fallen trees too, but the technology of those times could not detect them. These spheres were later found embedded in the tree resin. Their chemical composition, rich in nickel compared to iron, a property observed in meteorites, corroborated their extraterrestrial origin. The abundant distribution of these spheres throughout the soil sample also indicated an aerial disintegration of a meteoroid. Further studies discovered abnormal proportions of other metals in the spheres, amplifying the evidence of their otherworldly origins. Anomalies consistent with an impact event were detected in the chemical analysis of peats from the region. The isotopic signatures of carbon, hydrogen, and nitrogen at the 1908 layer of these bogs were found to be incongruent with the adjoining layers. Moreover, these discrepancies were not observed in the bogs away from the impact area. This layer of the bog presented a high proportion of iridium, just like the iridium layer at the Cretaceous Paleogene boundary. It was inferred that this resulted from the debris of the impactor having deposited in the bogs and the subsequent acid rain depositing nitrogen, believed to be a result of the explosion. Despite the apparent evidence, some scientists challenged these findings, pointing to similar isotopic compositions found in Tunguska peat layers from the T event, matching those of C and Cam carbonate chondrites in few reports. Observations of iridium anomalies were also cited to rebut these findings. The primary scientific theory for the explosion posits the occurrence of a meteor airburst, about 6 10 Chem 4 6 Min, above our planet's crust, attributed to an asteroid. It's common for meteoroids to enter the Earth's atmosphere daily from outer space at a minimum speed of 11 km, 7 miles. As these meteoroids journey through the atmosphere, the immense compression of air in front of them generates enormous heat, causing most meteoroids to burn up or explode before landing. The Tunguska airburst's initial energy estimates varied from 10-15 megatons of Tin-42, 63 petajoules, to 30 megatons of Tin, 130 pj, measured based on the object's estimated burst height and the scaling laws derived from nuclear explosions. Contemporary calculations incorporating the object's momentum highlight that a larger portion of energy was directed downwards than what could be anticipated from a nuclear explosion, estimating the airburst to have energy ranging from 3 to 5 megatons of TNT, 13 to 21 pg. The 15 megaton Ipst represents an energy level 1,000 times greater than the Trinity's and almost similar to the energy of the 1954 U.S. Castle Bravo nuclear test, measured 152 MT, and a third of the Tsar Bomba test conducted by Soviet Union in 1961. A study in 2019 posits the explosive power of the Tunguska event to be around 20-30 megatons. Since the mid-20th century, stringent monitoring of Earth's atmosphere has suggested that asteroid airbursts possessing energies equivalent to nuclear weapons occur regularly. However, Tunguska-sized events measuring approximately 5-15 megatons are rarer in comparison. Eugene Shoemaker speculated that 20 kiloton events happen annually, and Tunguska-sized events might occur once every 300 years. Current estimates suggest Tunguska-sized events to happen once every 1,000 years, with 5 kiloton airbursts averaging about once per year. These airbursts are generally considered to be the result of asteroid impactors, rather than the more fragile cometary materials based on their typical penetration depths into Earth's atmosphere. The largest asteroid airburst recorded using modern technology was the 500 kiloton Chelyabinsk meteor in 2013, leading to shattered windows and meteorite production. In 2020, Russian scientists used various computer models to study the passage of asteroids of 150 meters in diameter at slanting angles across Earth's atmosphere. These models incorporated various assumptions. Considering the object composed of iron, rock, or ice, the most accurate model resembled the observed event, which was an iron asteroid up to 200 meters in diameter, traveling at 11.2 km per second. This asteroid reportedly brushed off the Earth's atmosphere. Returning to a solar orbit, the explosion's impact on the proximal trees was akin to the effects of conventional Operation Blowdown. The trees, positioned directly beneath the explosion, have been stripped as the blast wave moves vertically downward, yet remain upright, while trees positioned farther away have been toppled since the blast wave reaches them traveling nearly horizontal. In the 1930s, British meteorologist and mathematician F.J.W. Whipple hypothesized that the Tunguska meteor was a small comet. This theory was supported by the glowing skies, possibly an effect of dust and ice dispersed from the comet's tail across the atmosphere, observed across Eurasia in the days after the impact, eventually gaining general acceptance among Soviet Tunguska researchers in the 1960s. Slovak astronomer Lubor Krzak in 1978 speculated that the meteor was a fragment of the periodic comet Encke, known for causing the Beta Taurids, an annual meteor shower that occurred around the time of the Tunguska event. The trajectory of the Tunguska object also aligned with that expected from a fragment of comet Encke. It is now understood that such bodies explode regularly above the Earth, a phenomenon observed for decades by military satellites. In 1983, Zdeněk Sekanina, an astronomer, refuted the comet theory, arguing that if the Tunguska object was indeed a comet, it would have disintegrated traveling at such a low altitude. He suggested an asteroid as the possible source of the object. This asteroid theory received further support in 2001, when a group of researchers led by Farinella and Fostini calculated an 83% probability that the Tunguska object had likely originated from the asteroid belt and a 17% probability of a cometary origin. However, the asteroid hypothesis faces a significant challenge. If the Tunguska object was a rocky asteroid, it should have left a major crater at the impact site, but no such crater exists. It is suggested that the asteroid possibly disintegrated in a massive explosion due to high atmospheric pressures and temperatures, leading to complete destruction with no large remnants, scattering material across the upper atmosphere and possibly causing the sky glow. 1993, models proposed that the asteroid may have been around 60 meters, 200 fa, in diameter with properties between an ordinary chondrite and a carbonaceous chondrite. Carbonaceous chondrite material would typically dissolve in water unless frozen, positing a challenge for this hypothesis. Chronicles of investigations into the Tunguska Event of 1908, an immense explosion in Siberia, narrate a scientific journey marked by diverse theories and consistent findings. In the latter part of the 20th century, Italian scientists, spearheaded by the acclaimed physicist Giuseppe Longo from the University of Bologna, extracted resin from the region's trees. Their analysis uncovered traces of elements predominantly found in asteroids, suggesting the cause to be a rocky, celestial body. A different theory was proposed by Kelly et al. 2009, attributing the event to a comet. Their argument hinged upon the noctilucent clouds sighted after the impact, a spectacle evoked by considerable amounts of water vapor in the upper atmosphere, akin to the exhaust trail from NASA's Endeavour space shuttle. Concurrently, Russian researchers presided by Edward Drobishevsky flagged the asteroid 2005 MB56 as the potential parent body of the Tunguska object due to its close proximity to Earth 3 days prior to the event. Scrutiny of fragments from the Tunguska site in 2013 by a joint US European team indicated a possible iron meteorite. Subsequently, data from the 2013 Chelyabinsk-Bolide events enabled the creation of newer models, surmising the Tunguska impactor to be a stony body, measuring between 50-80 mm diameter and striking the Earth's atmosphere at a blistering speed of 55,000 miles. As for the immense energy released, it was equivalent to the 1980 eruption of Mount St. Helens. The team concluded that such colossal impactors strike Earth only once in every few millennia. In 2007, a twist in the investigation came when scientists from University of Bologna pinpointed a lake in the Tunguska region as a probable impact crater. They proposed that a fragment of the Tunguska body survived the explosion and hit the ground, forming Lake Checo. Discrediting past studies that had deemed the lake to have existed for 5,000 years, they supported the recent research that proposed the lake to be 100 years old, aligning it with the time of the Tunguska event and fueling speculations about the cause of this phenomenon. Originally positioned within a stone's throw from the epicenter of the infamous 1908 Tunguska explosion is the seemingly innocent body of water known as Lake Checo. The lake has long been suspected as a mark left by a stray fragment of an extraterrestrial body, a theory that was investigated through the analysis of sediment cores extracted from the lake's depths, a core of 175 km, 69 in. From the lake's epicenter unveiled a meter-long, 39 in sequence of lake deposits sitting atop a chaotic mixture of coarse materials. The transfer from the lower to upper arrangement coincides with the time frame of the Tunguska event, as indicated by radioactive isotopes 210P and 130 Savanks. An inspection of aquatic plant remains in the post-1908 sequence revealed their abundance, absent in the pre-1908 stratum, suggesting that Lake Checo was birthed at the time of the Tunguska incident. Furthermore, dual distinct units are unveiled through pollen assemblages above and below the approximately 100 km level. The upper section, home to various forestry pollens and an ample amount of water plants, was presumably deposited under lake conditions akin to present times. Conversely, the lower unit was abundant in forestry pollen with a conspicuous absence of water plants. The prevalent theory suggests a marshy taiga forest occurred. Then, instead of a lake, reduction in taiga forest noted from the core's bottom upward was possibly due to multiple fires. Further drives the theory that the formation of the lake was around the same period as the Tunguska event. However, research in 2017 by Russian scientists refuted the theory that the Tunguska event brought about Lake Checo. Soil studies gave the lake an age of 280 years old, considerably older than the event itself. The sample they extracted from the lake's bottom showed yearly sedimentations that conflict with past calculations, suggesting that the lake timeline stretches far beyond the Tunguska incident. Parallel to this, impact physics also present their challenges, implying that it's implausible for a stony meteorite of an appropriate size to retain enough power after surviving atmospheric entry to create a crater as sizable as Lake Checo. The Tunguska event, a historical incident wrapped in mystery, could possibly have been caused by something related to the Vernay shot theory, as suggested by several hypotheses. Other researchers, alternatively, have delved into geophysics to find an explanation for this baffling phenomenon. A mirrored incident of a lesser magnitude unfolded on February 15, 2013, in Chelyabinsk, an inhabited area in Russia's Ural district. The explosive source was identified as a meteoroid, precisely an asteroid of about 1720 meters II-56, 60 in diameter. With an estimated initial weight of 11,000 tons, this asteroid exploded with an astounding energy equivalent of around 500 kilotons. Its burst in the sky, however, was not harmless. It injured over 1,200 people, mainly due to shards from window glasses blown out by the powerful shock wave it created.